Hello viewers, welcome to the session on convolutional neural network. In this session, we will get deeper into the main elements of CNN architecture. As you know, the convolutional neural network is a class of deep learning model which consists of multiple layers including convolutional layer for feature extraction, pooling layer for downsampling, and fully connected layer for classification. Let us explore each of these layers in detail. The first layer is the convolution layer. There are few things to learn in this layer are filters and the strides. We will see each of them in brief with the example. Coming to the filters, which is also known as kernel, is a small matrix used to extract special features from an input image or a volume of data. Let us understand the main factors of the filter. The first, the size and the dimension. The size of the filter is determined by its dimension, typically represented as m cross n, where m and n are the height and the width of the filter. Common filter size used in practice are 3 cross 3, 5 cross 5 or 7 cross 7. The filter shown here is of size 3 cross 3. Next, the weight of the filter. Each element in the filter matrix has a weight associated with it. These weights are learned during the training phase of the CNN and are adjusted through the process of backpropagation. In this example, the weights are initialized as 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1. The filter is applied to the input data through a mathematical operation known as convolution. This involves element-wise multiplication of the filter values with the corresponding input values, followed by the summation of the result to obtain a single value. This represents the feature or the pattern. In this example, you can observe that by performing convolution operation, the first entry in the matrix is calculated as 6. What has been shown here is a part of the input data. Similarly, the other entries of the matrix are calculated by performing the convolution operation. The convolution operation moves the filter across the input data in a sliding window manner and performs the calculation at each position. You can observe how the convolution operation is performed with the filters with a sliding size of 1 to get this feature map. This allows the CNN to capture the different patterns within the input. In the example shown, we have only one filter used, but multiple filters are typically used in each layer of CNN, each with its own weight, enabling the model to detect a diverse range of features. Let us know the few important points at this juncture. Basically, the network learns the weights through learning. The filter weights are adjusted to recognize the most relevant patterns for the given task, whether it is image classification or object detection or any other task by which the CNN is designed for. The collective application of the filters and the subsequent layers in a CNN allow for hierarchical feature extraction. This leads to effective learning and representation of complex features from the input data. Coming to the striding, in the context of convolution neural network, it refers to the step size or the increment size. The stride size is a hyperparameter defined by the user and indicates the number of units the filter moves with each step during the convolution operation. A stride of 1 means the filter moves 1 unit at a time. A stride of 2 means it moves 2 units and so on. When applying a filter to the input, striding determines how much the filter moves horizontally and vertically after each convolution. In the example shown, the stride size is 1. Striding affects the size of the output layer. A larger stride reduces the size of the output. Consider when using a stride size greater than 1 in convolution operation, jumps over the multiple pixels in the input data, reducing the resolution of the output. This can be useful for downsampling the feature maps and thus reducing the computational complexity and focusing on the most essential features. The smaller stride preserves more of the spatial information and it is better in capturing finer details. The stride size is a combination with the filter size and the input size affects the dimensions of the output feature map. Thus, striding is an important aspect of CNN architecture, influencing the balance between the spatial resolution, respective field size, and the computational efficiency. Next, let us move on to the pooling layer. The pooling layer are the fundamental components of the convolutional neural network and plays a crucial role in reducing the spatial dimension while preserving the important features of the input data. The common pooling operation include max pooling and average pooling. Let me illustrate the working of the pooling layer with a simple example. Consider a 2D array representing a feature map, which is the output from a convolutional layer, and assume a stride value as 2, 2. Here is how the max pooling operation works. Place a 2 cross 2 pooling window at the top left corner of the input feature map. Take the maximum value from the pooling window. In this case, for the first window, the maximum value is 7. So, 7 is placed in the output. As in this example, we have assumed a stride of 2. Repeat the process by moving the pooling window by a stride of 2 and take the maximum value from each window. In the average pooling, the average of all the values from the pooling window is taken. In this case, for the first window, the average value is 3, so 3 is placed in the output. As in this example, we have assumed a stride of 2. Repeat the process by moving the pooling window by a stride of 2 and take the average value from each window. The resulting output from after the max pooling is reduced size feature map with the maximum values from each pooling window as 7, 3, 9, 3. Similarly, the resulting output after the average pooling is a reduced feature map with the average values from each pooling window as 3, 1, 4, 2. The pooling has the advantage of making the representation more compact by reducing the spatial size of the feature map, thereby reducing the number of parameters to be learned. Pooling reduces only the height and the width of the feature map, not the channels. On the other hand, pooling also loses a lot of information, which is considered as a potential disadvantage. Next, let us see about the flattening layer. Before feeding the data into the fully connected layer, the output from the previous layer is flattened into a one-dimensional vector. The flattening is not a standard layer neural network, but rather a conceptual step in preparing the output of the last convolutional or pooling layer for input into a fully connected layer. The output of the preceding convolutional pooling layer is typically a 3D tensor with dimensions like height, width, and depth. The flattening layer simply flattens the 3D tensor into a 1D vector by unraveling all the values, essentially converting the spatial dimension into a single dimension. In this example shown, you can observe that how a 2D tensor is converted into a 1D tensor by a process of flattening. Next, let us move on to the fully connected layer. A fully connected layer is also known as a dense layer, is a type of layer in a neural network where each neuron in the layer is connected to every neuron in the previous and the subsequent layer. The CNN use convolution and pooling layer to extract features from the input data, and fully connected layer are used to learn high-level patterns and relationship from these extracted features. In the fully connected layer, each connection has an associated weight. That the neural network represents the strength of the connection. The weights are learned during the training process. Additionally, each neuron has a bias term, allowing the network to learn the best combination of the weight and the biases to make accurate predictions. Mathematically, each layer in the neural network would compute output is equal to weight into input plus bias. Next, let us move on to the output layer. The final layer of the CNN is the output layer, produces the network's prediction based on the learned features. The number of neurons in this layer corresponds to the number of classes. So in this example, there are 3 classes A, B, C. Therefore, there are 3 neurons at the output layer. If you observe so far, each layer, the network performs linear operations on the input data and passes the result to the next layer. So the entire network would then behave like a series of linear transformation. So without non-linearity, the entire CNN behave as a single linear model. Hence, there is a need to introduce non-linearity, which is done through the activation function. Let us see about the activation function in my next video. Bye bye. Have a happy learning.